Well, you guys ready? So we're gonna do a little more atomic theory. And so we've already done the lab where we actually looked at electromagnetic waves and all that stuff. Remember that? Where we were getting the lights excited, we were putting some energy in there and everything like that. Okay, now you get to learn about it. Right? That's how it works. Do it a little early, you get to learn about it later. Okay, so something is wrong with my screen. Okay, so energy basically comes in the form of electromagnetic waves. So we have gamma rays, we have X-rays, we have UV, visible light, infrared light, microwaves, radio waves, sound waves, you know. So all of those are forms of energy. And basically energy is going to always be transmitted at the speed of light, which is 3.00 times 10 to the 8th meters per second, which you guys already know because we talked about it already, right? And you guys have already done those calculations on the lab, right? That is due this Friday or this Sunday. So the thing that you want to know about energy, well, energy is going to be kind of composed of particles. So we know that electron is a particle, right? And the thing about that particle or light in general, it's going to be, it has dual properties. It has the property, particles of property, I mean, properties of particle and properties of wave. So it's going to act like a wave, and it's also going to have mass that's going to be associated with it. So when we think about energy, I'm going to add on another equation. E equals mc squared. You guys remember that? From the very beginning, where m is mass and c is the speed of light. Yeah, no, maybe. Okay. Also Einstein's equation. Right? Okay. C is the speed of light. Okay. So we've talked about this once before. So if I decided to throw a Sharpie at Lorenzo, right? So the Sharpie is pretty light compared to this. Let's say I throw these both at the speed of light. Which one's going to have the most energy behind it? The water bottle or the Sharpie? Okay. He's like, yeah, not on me. Okay. So how many of you guys believe it's going to be the water bottle? Okay. Why? It has more mass associated, right? So mass plays a part in energy, okay? And so a lot of times when we're looking at light, we're often looking at either electron or we're looking at, hey, you need some coffee, don't you? Or we're looking at something involved. I'll get you a packet in a minute, okay? So we know that the speed of light is equal to the frequency times the wavelength, right? Lambda is the wavelength, nu is frequency, okay? So we know the speed of light is always constant. Everybody remembers that, right? So it's not going to change. What's the speed of light again? But what is the value? It's right on the board, right behind me, right? So it's 3.00 times 10 to the 8th meters per second. So the only thing that's going to be changing is your frequency and your wavelength, right? Because we know that the speed of light is constant. So if frequency goes up, we would expect the wavelength to do what? Based upon this equation. Are you sure? You want to put money on it? So if this is going to remain constant and the frequency, nu, this little v, goes up, we would expect the lambda to do what? Go down. If it's going to remain constant, right? Okay. So they're inversely proportional to each other. As one goes up, the other one has to go down. Yeah, you can tell it's almost like a Monday, huh? Yeah, he's passed out, half asleep, struggling. He's nodding off. So now this figure is a pretty cool figure here. It tells us a lot here. So the wavelength here, when we have very, very small wavelength, we know that the frequency is going to be pretty high. So as the wavelength increases, the frequency gets lower, right? So you guys see that inverse proportionality to it, right? Okay, not only that, so you guys, gamma rays heard of the Incredible Hulk, everybody? Yeah. So gamma rays are so small. They're so small that they can actually go in your cell and chop up all your DNA and your cell particles and just destroy things, right? They're smaller than atoms themselves. So that wavelength, the distance between those waves are so small that they're able to do that. So that energy is able to sit there, go through your cells and destroy it. So gamma rays would do damage, major damage to us. Same thing with X-rays. So how many of you guys have taken an X-ray? Right? So don't they put a lead shield on you when they give the X-rays? Like on your mouth and everything, right? To kind of protect you from the rays themselves because it causes damage to your DNA, right? It destroys those particles of DNA because X-rays, in some cases, are even smaller than an atom itself. So this is the size of an atom. This is the X-ray range, okay? This is the gamma ray range. So gamma rays are known, they can actually destroy molecules and atoms and stuff as a result because they're so tiny, right? The energy better. Where do you find gamma rays? So yeah, actually the sun, close to the sun has gamma rays associated with it. Also, we've created gamma rays here on Earth in special facilities, right? So they have shielding for that. Some particles themselves, some elements will actually exhibit gamma rays as well too. Okay, so the UV light comes from the sun, right? And so we know that UV will actually destroy a virus because it's about the size of a virus. So it actually does damage to the virus, right? So visible light is from 400 to 700 nanometers. And that whole rainbow white light, this here, is all visible light. So that's all of those lights that are combined all together, okay? And so when you guys took the diffraction slide, you're able to see that rainbow because you're separating each of the different wavelengths that you're diffracting. And so you had a continuous spectrum, okay? So this is an example of a continuous spectrum. How do you have a look on your face? So what does that look? Disbelief, or you have a question? No, not yet. Don't worry about it. We'll get there. I promise. Okay, so we have infrared light. You guys are familiar with infrared light, right? So that's about in this range. And so that's about the size of a bacterium or animal cells that falls in that same range as that. We have microwaves. Microwaves are about the thickness of a CD or the width of a CD. And so microwaves that we use the microwave, we know that doesn't going to destroy our cells, right? It cooks our food, it warms those water molecules, but it doesn't destroy the water molecule. Okay, radio waves are about the size of a dog, right? So we look at that one wave, that wavelength is going to be about the size of a dog. And then we have long range radio waves. So those are much bigger. So the continuous spectrum was basically that spectrum of all of the colors, that rainbow. That is an example of continuous spectrum. A light spectrum is what you guys saw when we looked at hydrogen. You guys, how many of those bulbs did you think were hydrogen? Did you think at least one of them were hydrogen? Yeah, no, maybe. You guys did the experiment. You guys tell me. You didn't think any of them were? You don't remember. Okay, old age. Okay. Okay, so that was an example of light spectrum. I'll show you another example here, in a second. And so light spectrum basically gives us, line spectrum gives us very discrete lines, right? And so those discrete lines are a result of those electrons being excited at different levels. We're going to talk about that in a little more detail here in a second. So energy is basically going to be released by electrons that are being excited, right? And that energy that's being released by electrons being excited is called a photon. Okay, and I've already talked to you about the wave and particle duality, right? So a wave, right? You guys are all familiar with the wave, right? No, a wave, right? Okay, so the properties of a wave. So when we're talking about the wavelength represents from peak to peak or trough to trough, okay? As the wavelength increases in size, then the frequency is going to decrease. So we have two peaks here, right? Compared to down here, where we have a smaller wavelength, we have more peaks, so more frequency, okay? So that just basically shows us that they're directly proportional to each other. As the frequency goes up, the wavelength goes down, it becomes smaller, okay? Vice versa. So white light, when it's diffracted or dispersed, it forms that continuous spectrum. So that's what we're seeing here, our nice continuous spectrum. Here, basically, white light is shown through these little slits, and then you have a prism. So that diffraction slide acts as that prism, and it gives us that nice continuous spectrum where everything kind of blends in together. But when we excite an atom like, or an element like hydrogen, then we get very discrete line patterns, right? So discrete that every element is going to be unique. They're not going to have the exact same line. And you guys saw that when we looked at all of the 5 different elements, that they look exactly the same. Were you able to distinguish between them? Okay, good. So this is just basically showing you that line spectrum. So this is line spectrum of hydrogen, mercury, and neon. And you guys can see, so hydrogen has that 4 discrete lines, where mercury has much more than 4, and neon has even much more than mercury, right? So, and we can sit there and use that discretion, those discrete lines, to sit there and distinguish between the elements that we're looking at. Okay, so let's get to the part that's exciting. So there's this guy named Bohr. So Bohr basically said, not like I'm bored, I'm Bohr. Bohr basically said, he basically designed the model for the hydrogen atom. Now, he basically came up with the idea that, or used some of the information that was already being known, such as there's a nucleus. And he said that, well, there's these electrons that are orbiting the nucleus, right? And so those negatively charged electrons are orbiting around that nucleus. And then, but most of the atom itself is made up of empty space. And there's certain regions of that orbit that these electrons are going to be at. And they need to be there. And that represents energy states, right? So those are energy levels that kind of keep those electrons orbiting in that area, okay? And so this energy is quantized, not continuous. Continuous basically means that it would be running right into each other, right? Kind of like that spectrum. No, that energy is at certain levels. And so when you guys excited the hydrogen atom by when we plugged it in, and you guys saw that little, there's a red light and we saw the diffraction, we saw those 4 lines, right? That proves that it was quantized. That is not continuous, right? If we saw light like white light, then that would suggest that it was continuous. But we have very discrete energy levels that allows it to be excited. So this is basically showing you the quantum concept. So if it was continuous, you just have this ramp, right? Running into each other. But if it's quantized, you have steps. There's a step of energy for each one. And that's essentially what you guys saw. You had those 4 lines. For hydrogens, you saw discrete lines of energy. So Bohr basically said, this is what it looks like, right? This here is that first level of energy. We often will call that period 1, right? This is the second level of energy, period 2. Third level of energy, period 3. Fourth level of energy, period 4. And so the electron for hydrogen would sit at this ground state and is able to be excited to all of those other states. So if we put enough energy into it, we can pop it all the way out here, right? To that 4th energy level, right? And then as it crashes back down, because it has to go back down to the energy state, then it will release a photon and we'll get beautiful light of a certain wavelength, okay? And did you guys see that? Yeah? No? Okay, don't be so excited. Man, I'm thinking it's a Monday. You guys are dead. You're like, oh God, chemistry, wow. So that movement of electrons from one energy level to another energy level is called a quantum jump or a quantum leap, okay? So, and again, we're just exciting it. You guys remember we talked about, talking about your kids, your nieces or nephews, or when you give them a whole bunch of sugar, right? So when you give them a whole bunch of sugar, then what happens? I said sugar. So when you give them a whole bunch of sugar, what happens? And then what happens? They get way up and then they crash way down, right? So that's exactly what happened with your electrons. Right? They got way excited, right? You put that energy in there, pop them up, and then they crash down and you got those nice lines. Okay, so we get them excited. We put them in an excited state. And then we crash them down. Okay, kind of like another analogy. Have anybody popped off to you and got you really worked up, got you so pissed off, your ears were like steaming and everything like that, right? They just got up in your face, and you just wanted to say, you don't get me away from this person, I'm going to knock them out, right? And then you have to go take a walk around the building to calm down and, okay, so now I'm back to my ground state, right? So that's kind of like what's happening with the electrons. You get them all worked up, and then you get them back to that ground state, okay? So, in theory, how many of you guys have a turkey or eat turkey for Thanksgiving? I had a turkey this weekend. I'm thinking about food, right? You have a turkey? Yeah, I knew he was going to tell me. Yeah. So, in theory, if we excite your turkey the right way, your turkey could end up in my oven, right? If we excite all of his electrons the right way, he can end up in my oven and he can be cooked, right? But as soon as he comes back to that ground state, technically he should be able to go back to you. Now, so this is the theory of transport, right? So, the whole thing with transporter, like Star Trek and stuff like that. Yeah. So that is the theory of it. So in theory, we should be able to do that, but it's hard for us to sit there and excite all the electrons in a turkey at the same time to the right energy level so that we can do that. That's the part that we're working on, right? But in theory, on paper, it should work because we know we can excite electrons. Because we are not quite there, Yeah, so, and then also you need to figure out a way of exciting them all to the right level. So not so much that you burn the turkey, and it ends up in the right energy plane, right? So we're playing with it. It's a process, It's a process. Things don't happen overnight. Cars weren't built in a day, right? We're not cooking it. Well, if we try to excite its electrons, we may be cooking it, Okay, so but the idea is that we could sit there and put it on another energy level so that it would change its energy state. So in that case, the turkey could end up in my kitchen, right? In my oven, so that I can cook it, right? So Exactly. It goes like right where it started.
Like, go further or a little more below.
So there is some theories that sometimes it does go beyond below what it should, and then it levels off. And so it's kind of believed to do a little bit of both because there's resonance that's happening. And so, but it seems to be a very tight margin because based upon the lines, you get these really nice lines, right? So based upon the lines, it doesn't seem to travel too far off. So, but there's some theory that there might go a little bit lower than expected, but then it just kind of reaches an equilibrium, reaches a balance. So, okay, so let's see. So this is just basically showing that. This is our electronic ground state. We get it all excited. It absorbs that energy, pops up to that next energy level, and then stays there for a little bit. Then it drops back down. It has to go back to ground state. Yeah. Yes. Yeah. So in a sense of transfer, transfer. Yeah. Okay. So Bohr basically discovered that first quantum number. It's called the principal quantum number. It's that principal energy level. That's it. And it correlates to our periods. Okay. So on the periodic table, it's the numbers on the side. So it kind of represents those numbers. Okay. So there are 4 quantum numbers. They're going to represent the principal energy level. They're going to represent the sublevel, the orbit, and then the last one would be, it's actually the spin of the electrons in that orbit. Okay, so the principal energy level, as I told you, is going to be our periods. The sub levels are going to be S, P, D, and F. Now, the S sublevel has 1 orbital. The P sublevel has 3 orbitals. The D sublevel has 5 orbitals. The F sublevel have 7 orbitals. So if there's a G, how many orbitals would you expect it to have? Okay. That's right. So if there was a G, there would be 9. And if there was an H, it would be 11. Okay, now each orbital, this represents orbitals, each orbital can hold 2 electrons, one that's a positive spin and one that's a negative spin. And it's important that it is a positive spin and a negative spin, because if they're both positive, that causes destruction. It's not going to be a good thing. So then, how many electrons can the S subshell hold? 2. Number of electrons. Okay, what about the P? Okay. Yep, so you just multiply it by 2, right? The D, and if there was a G, it would be 18. And then if there was an H, it'd be 22. Okay. So are you guys good? Yeah. So each orbital can hold 2 electrons, one spinning one way and one spinning the other way. Okay, everybody got that? Good. Okay. So one second. So if you guys have your periodic table, whip it out. How are you guys doing at Hartnell? You guys doing good? Yes, sir. Can you what? Yes, you can. What are you sitting on? Yes, you can get a chair from the other room. Okay, so everybody got their periodic table out? Okay, so group 1 and group 2 are going to represent that S sublevel. Group 13 through 18 is going to represent the P sublevel. It's the sublevels. That's a P. This is an S. Yeah. Oh, it looks like a duck. I know. Group 3 through group 12 is going to represent the D sublevel. And then the actinoids and the lactinoids, these guys are going to represent the F. Right now, we don't have enough elements on our periodic tables. They haven't been discovered yet, those extra ones, to go to the G and the H. But we want to keep room for them because, you know, one day we're going to figure out there are other elements that we can stabilize. Yes. That's an S. An S. Yeah, let me make it look like an S. My S is kind of like 5, so. Okay, so this is an F down here. Okay, so how many electrons can the S orbital hold, or the S sublevel? 2. 1, 2. How many can the D? 6, right? Because there's 3 orbitals, and each one could hold 2 electrons. 1, 2, 3, 4, 5, 6. I'm sorry, the P. Did I say the D? Sorry, P. My bad. P. And how many can the D? 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And the F? 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Now, these two are part of the D, and they actually sit right here in this area. Really, what the periodic table should look like is like this. Hold on. Okay, so the F is actually between the S and the D, and so it sits right here. And those 2 electrons are actually, I mean, those 2 atoms are actually in the, they would fall in the D. So to make the table actually fit on a regular sheet of paper rather than having to get a bigger sheet of paper. Okay. And then it also means that you can get it all on one little sheet rather than, yeah. Okay. Okay, so when we do electron configuration is just keeping account of all of the electrons in an atom. We want to know the electrons that are there so that we can determine how many that are going to be available for us to sit there and take, to give, to share, right? And how many of them are going to be used to help define that element, right? Okay. So let's say we'll start off with hydrogen. Hydrogen and helium. Hydrogen has how many electrons? It has one. Right? So when we write the electron configuration for hydrogen, we just put that element, hydrogen, and you use the principal quantum number, which is that period. So that'll be 1. Oops. The subshell is an S. And how many electrons that we have there? You guys told me 1. So that would be the electron configuration. Okay. So that first number tells us the principal quantum number. The letter tells us the subshell. And that superscript tells us how many electrons there are. Okay. So helium its electron configuration is 1s2. Even though it's over here, it really should be over here. But because we have other things that the periodic table is telling us, we just have to know that helium has 2 electrons. And we know that the S sublevel can hold 2 electrons. Okay. So if I have an element like carbon, the electron configuration for carbon would be 1s2. So that would be the first 2 electrons. And you always feel from the lowest energy level. So you always have to start off at the 1s. Right? Then 2s2. And then 2p2. Okay, so that accounts for every electron that carbon has. Okay, are you with me? Kinda. Okay, so let's try one more and then we'll see. And then I'm going to throw a curveball. So I always have to throw a couple curveballs, right? So let's do phosphorus. Okay, so phosphorus has a total of how many electrons? 15. So we start at the lowest energy level. We start at the 1s. S is lower than P, which is lower than D, which is lower than F. So 1s, 2, so that counts for here and here. Then we have 2s2, which is here, here, and then we have 2p6, 1, 2, 3, 4, 5, 6. Then we have 3s2, and then we have 3p3.
The numbers in front of like the S and the P is based
off the periodic table, the periods, right? Okay. Yeah. So if we count the subscripts, that's 2, that's 4, that's 10, that's 12, That's 15. 15 electrons, right? Yes. Yes. Yeah. So what it is that they're spaces, right? So they're just kind of representing. It's kind of like orbitals are kind of like little love seats, right? They're empty love seats. And then as you have more and more electrons, you have to fill up the love seats that are like all the way up in the front to the love seats that are in the back. So like, let's say we have a movie theater. They're in groups of twos. The S's have one love seat. The P's has 3 love seats. The D's have 10 love seats, right? And our theater is kind of set up in a certain way so that it fills up. You always fill up in the beginning and work your way up. So in the case of phosphorus is over here. So then you want to fill up these first love seats first. So that's the 1s, right? So 1s2. Then you fill up your next set of love seats. Then your 2s2. And then there's 3 love seats that are for the P. So we're just calling them all P. So then that's 2p6. And then we have 3s2. And then 3p, whatever's left. Bromine. No, you still would have to, because they're still going to be grouped into pairs of 2s, right? So they still have to be accounted for. But you would have all of these that would be in the P. All of these would be in the D. Okay. And we'll do bromine here in a second because there's going to be a little bit difference with bromine compared to the others. Yes, ma'am. We will get there. Don't cheat. Come on, give me a chance. She's getting all ahead, you know. Okay. So if we've done bromine, right? Let's say we're going to do bromine now. Now, the thing is that this here, the d orbital actually will start at 3. Okay. The reason why the d orbital starts at 3 is because the 3d is actually lower in energy. I'm sorry, the 3d is higher in energy than the 4s. So 4s is less energy than the 3d. So then it kind of drops the level down. Okay. So then this guy starts at 3. This will be 4d. This will be 5d. This will be 6d. Okay. And then that's the same thing that happens with the F, but the only thing this here is the 4F. So we start down here at the 4F. So if we're doing bromine, which goes through the 3D, we have to take 3D in consideration. So we'll write out one for bromine. So it's bromine is Br. Okay. And I'm going to use a different color so you guys can start. So we have 1s2. Okay, so that accounts for that first set, right? Then it's 2s2. Then it's 2p6. One, two, three, 4, 5, 6. 3s2. Three p6. Then 4s2. Three d10. And then 1, 2, 3, 4, 5. 4p5. because the 4s in terms of energy, and it's all about energy. You always want to put electrons in the lowest energy shells possible. You always start from the lowest and build your way up. 4s is lower in energy than the 3D. It just happens that way.
Would it be 4 or would it be
39?
Yeah.
Yeah, so then 39, if we did 39, right? Then in that case, we would go, that would be 4D1. Yeah, yeah. So it would end on 4D1. Yeah. Okay. So does that make sense? Yes. Yeah, it would be 5. So this, if it was 39, it would be 4D1. It would be 5S2, then 4D1. Does it make sense? Okay. So now we have what we call a core and what we have called valence electrons. Now, the core represents filling up to the noble gases. Okay. So if we take a look, let's go back to carbon. Not carbon, let's do phosphorus. So if we go back to phosphorus, right? So phosphorus is right here. So the nearest noble gas before phosphorus is called neon. I'm going to erase this so you guys can actually see. Okay, so the nearest noble gas before phosphorus, here's phosphorus. So the noble gas that will be before phosphorus is neon, right here. So neon represents the core. And so these electrons right here, this is going to be your core. These electrons are going to be the electrons that we can play with, right? So those are called our valence electrons. Okay, so do you guys have a savings account? Do you have a checking account? Okay, so we put money in our savings account. Do we take it out? Are you supposed to take it out? Okay, so now we're going to be real about this, right? We know that we do, right? But you're not supposed to. It's supposed to be savings, right? You're supposed to leave it alone. Don't touch it, right? So that core is kind of like that savings account. We're not supposed to touch it. We're never supposed to touch it. But that checking account, oh, we can go to the casino with that. We can pay the bills with that. We can do all the things that we're supposed to do with that, right? And so we're able to sit there and use that at our discretion. So the valence electrons are kind of, right? Those are the electrons that we're going to be using for bonding or making bonds. So you're going to either share them, you're going to give them, you know, or you're going to try to add more to them, right? So those are the electrons that you can sit there and play with for bonding, okay? And so those are the electrons that are typically excited, right? You know, easily excited, because it takes a lot more energy to excite that core, okay? So because of that, we often will just write this as, in terms of electron configuration, we write it as P, that noble gas, and then the valence electrons. Okay, so, and it also, it's a much shorter way of writing it, and you don't have to write all of that little part out. You just go to that nearest noble gas that's before the element, you write that into brackets, and then you just write the electrons that would be used, that you're able to sit there and use for reactions. Okay, so you guys with me so far? That's going to be, yeah, you're going to use that as in brackets first. And then you just look at the ones that are afterwards, right? That's right. So we had chromium, right? Okay. So then in that case, this here is going to be our core. All of that's going to be our core. So it would be the one that would be before bromium. Bromium is right here. So it would be argon, right? So then what we would do, we'd write Br dot dot bracket argon. Then we start at argon, it's 4s2. (3d10) and 4p5. Okay. Much easier, right? Okay. So let's go back to our lecture notes and then we'll come back here and do a couple more. Okay, so we've talked about those sublevels. So we have the S, the P, the D, and the F. We've talked about how many electrons that each of those sublevels could actually hold. So when we talk about those periods, so we have the second period, right? That has the S and the P. Well, the S is lower in energy. The 2s is lower in energy than the 2p. The 3s is lower than energy than the 3p, which is lower than in energy than the highlighter. The 3s is lower than the 3p, which is lower than the 3d. And in the case of the 4s is lower in energy than the 4p, than the 4d, and then the 4f. Okay, and this is just basically showing us that, right? So remember when I told you that 4s is lower than in energy than the 4d, and that's the reason why we load up the electrons there first before we go to the 3d. So that's why we have to start at the 3d, okay? Because it's lower, 4s is lower in energy than the 3d. So when you're adding electrons to it, you always want to do the lowest energy first. 4s is lower than 3d, so that's why we do that. Okay, we've talked about orbitals, right? So the S sublevel has one orbital. It holds 2 electrons. The P has 3. The D has 5, and the F has 7. And like I said, if we add a G, it would be how many? G? 9. Yeah. Okay, so now Bohr basically had said that the electrons are orbiting the nucleus, right? And he just kind of generally said, okay, it's orbiting the nucleus, kind of like how the Earth orbits the sun, right? But in reality, that's not the case. It has very defined orbits. The electrons that are in the S orbital, they orbit the nucleus like this. So they make a perfect sphere, right? Those that are in the P, they look like dumbbells, right? So this would be in the X direction. This would be in the Y direction, and this would be in the Z direction. So this is the one orbital for the X direction, one for the Y direction, and one for the Z direction. That's the S.
No.
This one here? So that's the P. That's one of the orbitals for P. P has 3 different orbitals, one for the X direction, one for the Y direction, and one for the Z direction. Right? So the D gets a little more complicated. You got this crazy, donut and 2 balls on top, or balls on top and balls on bottom. So that would be one orbital. This here, that would be another orbital. And we call this guy dx squared minus y squared. This one here, this one's called dxy because it's in between the d and the y. This one here is called the dyz because it's in the dyz plane. And then this one is in the dxz because it's in the xz plane. Okay. This one says dz2. Yes. Okay. Now the F sublevel has 7, and they're a hot mess. And so there's some discrepancy in terms of what they actually look like. So your book says, oh, we're not going to show it. You know, lately we've gotten one image of what it should look like, and it's based upon the energy signature of electrons that would be found there. But nobody knows for sure, right? And so they're guessing, yeah. So just an educated guess. So, have you guys seen Russian dolls? Russian dolls? So you have one little doll inside of another little doll, inside of another doll, inside of another doll. You ever seen that? You have seen that? Okay. So those are, well, I call them Russian dolls. I don't know what they're really called. But, so now the orbital, the sublevels act like Russian dolls. So if we have the 1s that's surrounding the nucleus, so the very big center would be the nucleus. Then we have one doll around it, right? So that would be the 1s, right? And then we have the 2s that would go on outside of that one. And then we'd have the 3s that would go on outside of that one. So as we go down the periodic table, right, it's going to get bigger. The element is going to get bigger because there's more electrons around it. So you're just adding a layer, a layer, a layer, a layer. Okay. So if we sit there, we think about it as we go down the periodic table, the element is also going to get bigger in size. It's also going to put another layer of energy associated with it. So the higher the energy it is, right, typically the more uncomfortable it is, the more it's going to be willing to react. Okay. So because it wants to get to a lower energy state, kind of like you guys, right? Don't you guys want to be nice and comfortable and rich, don't have to worry about anything, just sit up and drink mimosas all day, right? Right. So, I mean, electrons want to do exactly the same thing. And so its goal is to try to find a way to get to the lowest energy state to have stability, right? Okay, so are you guys kind of getting this so far? So far? You're stuck on the Russian dolls? Okay, let me see if I can find a picture of a Russian doll. Yeah, but it's just the concept of you're adding a layer. So this will be 1s, so this would be 2s, this would be 3s, this would be 4s. And so each period, so as we go down the period, it's going to get bigger. You're adding another layer to it. Okay. So we have Pauli exclusion principle. Pauli exclusion principle says it's pretty simple. It says that in an orbital, you can have at most 2 electrons. Okay. In an orbital, you could have at most 2 electrons. You could either have 2 electrons, you could have 1 electron, or you could have no electrons. You can't have more than that. Okay. That's pretty much what it says. Okay. Yeah, you could have 2 or less. Because an orbital, if you have more than 2 electrons, because they can have to be opposite spins of each other. If you have another electron in that orbital, it'll throw off those electrons and it'll cause an explosion. Right? No, they're opposite spins. Yeah, but they have to be opposite spins, right? But it can only hold 2. So each orbital only holds 2, right? Nope. Nope, because then you have 2 of them that are in the same spin and they can collide with each other. Yeah, they're all one. Yeah. Yeah. Okay. Oops, got carried away. Okay, so if you take a look at the periodic table, this basically shows you the order that you're going to be adding those electrons, right? So here you have that 1s, the 2s, 2p, 3s, 3p, 4s, 3d, right? 3d, 4p, 5s, 4d, 5p. Now, when you get down here at the 6s will actually shoot down to here to the 4f, and then we'll shoot back up to the 5d. Okay, so let me show you that. Okay. So if we have, let's say we have europium, 63. Okay. So if we do the electron configuration for that one, we're going to do it the short way, right? So we'd want to find the noble gas that would be right before europium. Europium is 63. So what would be the noble gas that would be before 63? Xenon. 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 Yeah. So for europium, we'd write EU. Bracket. XE. Okay. Then we're in the 6th period. So it's 6s. 6s2. Then we'll go down here. And if you follow the atomic number, it'll keep you from doing silly things, right? 6s2, 1, 2, 3, 4, 5, 6, 7, 4, F, 7. Okay. You guys see that? Okay, so let's do one a little more complicated. Let's do lead, 82. If you needed a lead, PB, lead. Okay. Lead. Okay, we're doing lead. Okay, and we're going to do it with the core and then the electrons that we can play with. Everybody wants electrons. Yeah, question. Okay, so what is going to be my core? This one? Okay, so xenon, XE? Okay. Okay, then, so this is where we're starting. Then 6s2. Okay, so that takes care of this. Then 4f14, right? 14. Remember, these last two are really part of the D, right? So 4f14. Okay, so then we come down here. That's 14 right here. 1, 2, 3, 4, 5, 6, 7, 9, 10, 11, 12, 13, 14. We know that this one is really part of the D, right? So then it's 5d10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's 5d10. And 6p2. Yes.
I got everything, but I'm a little confused on the 14. So I know it's the bottom, but how do we get the 4?
Because 4f is higher in energy than the 6s. So it shifts. So if you just, the way that I always remember it is, I always remember it shifts by 2. The F shifts by 2. The D shifts by 1.
Okay.
Yeah. Or I just put it on my periodic table. So then I always know that this guy is always going to start at 4. This guy is always going to start at 3. Okay. It's about energy, because the electrons have to be put in the lowest energy state first. So you always want to stack the lowest one first, and then you have to go up to the highest, because you want to keep a low energy profile. If you stick them at a higher energy level, then they don't like it, right? And so they're going to push themselves back down there, right? Because remember, the whole concept is to keep a low at ground state, right? If you're not putting them in the low energy, they're not at ground state. That's kind of like you're getting kids already hyped up on drugs, before you even give them candy, right? So that's not a good thing, right? Yeah. Before you give them candy, yeah. Okay, you hype them up on candy before you give them drugs. Okay, yeah, is that a better analogy? Yeah. Okay, does that make sense? Yeah, I mean, you want to think of it as it's all about low energy, right? You don't want to use too much energy, right? And if you put them at a higher energy level than what they're supposed to be at, then yeah, they're going to drop down anyway, right? And so you want to try to keep them at that low energy, because they're trying to get to that low energy, right? They want to stay at that low energy. And the 4F is a lower energy state. I mean, it's a higher energy state than the 6D. It just because there's an overlap between it. It's they call it degeneracy in chemistry, and so there's a whole field that's dedicated to that study. Understand that that energy state is actually higher than the 6. Yes, so 7 would be 5F. That's right. Yeah. So like this here, again, is going to be 3D. Yep. This is going to be 4D. And we know that this is 5D. And then this down here is 6D. Yep. And then this is 4F, and this is 5F. Yep. And so if you just, like I said, if you look at the paper, right? I think it's page, I don't know, 31. It's slide 31. So divide that by 3, it's like 11, page 11 or something like that.
But
yeah.
Right
Yeah,
now,
that
on this picture at the end, the last two are pointing to the F, but they're not.
They're not, no. But that's because they already put the ones in D. They only have 14 that are there, right? If you count it, they put So this
Oh, they moved
periodic
them
table,
already? Oh,
yeah, they've already moved up there. Okay, so let's do one more, and then I'm going to teach you something else. Let's see. Uh, let's do Hasium 108. Okay, so it's radon. 7s2. 5f14. 66. Okay. Okay. You guys got that?
That's so much easier.
Yeah.
Yeah.
Okay. So now we know that we also will be working with ions. Ions are what again? What is an ion? It's charged atoms. Okay. So how do they become charged? Do they add an extra proton? So we're either adding electrons or we're losing electrons. Okay. So if I have HS 2 plus, which electrons am I going to take away? Okay. Now, the way that this works is that even though these guys are lower in energy than the 5F, right? We're going to take away from the highest level, right? So 7 is higher than 5. Would you agree? And that's because of location. So in reality, even though it's lower in energy, where it's located at, it's located further out, right? And so you're going to take away from the ones that are further out compared to the ones that are closer in. Okay. So then if we're taking away 2 electrons, we're going to take them away from the 7s rather than the 5f or the 6d. Okay. And the analogy that I think of is, if you have a mom who has a whole bunch of kids, right? The ones that are really close to her, right? That she keeps right next to her, right under her arms. And then you have the kids that are across town. Now, if somebody's going to steal kids from her, which ones are they going to steal from? The one across town, right? Because they're not right next to the mother, right? And so the nucleus is kind of like that mother. It's keeping those electrons really tight to it. The ones that are further away are not kept as tight. They're easier to pluck. That's right. And that's because they're on the outer shells. Yeah. That's how it happens, right? And it makes sense because the electrons are further out, even though energy wise, they could be lower in energy, right? Okay. So in that case, this ion would have this electron configuration. 5f14. 66. Okay, where it's removing 2 electrons from the 7s. What was that? That's why there's no more. Yeah, so it's all gone because there's none there, right? Because you're removing both of them. It's both, right? Because if there's nothing there, then there's nothing there, right? Because it only holds two. Okay, so if it was, you're saying that if it was HS, we'll say 4, right? HS 4 plus. That means we're moving 4 electrons. So then we would take 2 from that 7s, and then we would take the other ones from the 6D, right? Because 6 is further out than the 5. So again, you have to think of it as shells, right? So it's easier to take from the outer shell, even though lower energy, you can take from the outer shell because it's easier to get to. Okay. So this guy would be Rn. Five F14, 6D4. Yes. Yes. Yep. Yep. So we're doing gold and gold 3 plus. Okay, so what should be our core? What should be our core? Xenon. Xe. Struggling there. Okay, too much candy. Yeah, no, you guys thought I was going to say something else, right? Okay, so, and then, so that brings us here. 6s2. And then 4f14. And then 5d9. Everybody always forgets to count this one first. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so the ion, what would that be? Xe. Or F14, because we're taking away the 6s2, and then 5d8. That's right. Okay. Are you guys with me?
I'm always with you.
Okay.
Well, I'm gonna give up on that. Don't worry.
That's important. Okay. Okay, so let's go ahead and move forward. And if you guys need some extra help, Cole will hook you up with office hours, right? Or with tutoring hours. And Parnell, you guys have Gabriel. Okay, so remember when I told you that this is basically an energy diagram? where they actually track a single electron and find the density of where it's located at. And so kind of based upon this, this is part of the D orbital. Remember that donut hole? And yeah, so yeah, that's in the middle. And then if they had shown the full thing, you'd have saw the two lobes up top. So yeah, it looks exactly like this, but then there's, because this is only kind of, yeah, in the middle. They didn't show the upper parts. So you'd have the two bulbs up top. So okay, so again, that first number is that principal number. The letter tells us the sublevel, and this tells us how many electrons that are in that sublevel, okay? This is just the electron configuration for some of them using the core system, right? Okay, we've talked about the core and how to use the core. And so this is just basically showing you, this is the neon core. This here is the argon core. Okay, this basically goes through what I went through, explaining how to write the electron configuration. So these guys are exceptions. Remember I told you there's always exceptions in chemistry? These are exceptions, okay? Chromium and copper are two exceptions, and there are a couple more. So just know that they're exceptions. If you write the electron configuration the way that I've shown you how to do it, I'm not going to deduct you for not knowing that these guys are exceptions, but you have these two exceptions. Just try to remember that. Okay, so write the electron configuration for fluorine, which its atomic number is 17. So, and I'd like you guys to write it the long way and then the short way. Both. You like the long way? You don't like the long way? Okay. Relax, relax. Don't rub off your eraser. Okay, Johnny, you're gonna help me out here then. So long way. So we have Cl. Yeah, long way. 1s2, 2s2, 3s2. Are you sure you're not missing anything? On the other side. So remember, go all the way across. What's it gonna? You have 2s, and then you have 2p6. Okay. Let's see if I get my pen over there. 2p6. And then 3s2, then 3p5. Okay. Oops. Okay. The short way. Neon. Okay. Okay. Piece of cake. Okay. Okay, you guys over here? Good. Everybody ready to move forward? Okay, cobalt. So let's write the electron configuration for cobalt. Cobalt. Let's do it the short way. Okay. Okay, so what's going to be the core? AR. Okay. Where's 2? Okay. Questions? Okay. So what if we had cobalt 4 plus? What would be the, are you sure?
Yeah.
No, we're going to take out 4s2. He's right, it's 3d5.
Oh, you're trying to confuse me. Are you sure?
I wasn't trying, no,
Oh,
no,
thought had
I
it.
just wanted to make sure you're sure. You have to be confident, right?
I'm over there getting pat down because I didn't know my course paper was going out. They were like with me. He's like, "Are you sure these are them?" I'm like, "Dude, I
Okay.
don't know." I'm over there pat down like I'm smuggling narcos or something. This little white boy scared. I'm over there like, "Please, sir, don't take me." It was so bad.
Okay.
My mom was watching me like, "What are you doing?"
Okay. So we've talked about valence electrons, right? So electrons, those are going to be the electrons that we're going to be able to use. We're not going to use those core. We're going to use the ones that are extra, right? Now, when we start talking about reactions, right, we mainly start talking about the valence electrons that are in the main group. So it's going to be basically the group 1, group 2, which is going to represent that S and that P, okay? Because that's going to be our outer shell. Those transitional elements, right? We typically don't talk too much about those in terms of the reactions. We mainly talk about group 1, group 2, and then group 13 through 18, okay? So let me kind of put that in perspective here. Okay, so we're talking about the S and the P. If you count all the electrons in the S and P, they represent 8 electrons, right? 8 oct, okay? So when a noble gas is considered to be noble because its outer shell is full. That means its octet is full. So elements want to try to get their octet full, except for these transitional metals. So like right now, we're going to basically kind of ignore these guys, right? Just a little bit, okay? So we're going to be looking at the S and the P, okay? And so that's going to represent our octet. That's that outer layer, okay? So How many valence electrons does group 1 metals have? Somebody said 1. I heard 1, right? That is correct. They have 1 valence electron, right? Group 2 metals have 2 valence electrons. Group 13 have 3 valence electrons. Group 14 has 4 valence electrons. Group 15, 5. Group 16, 6. And group 17 has 7 valence electrons. Okay, so we're just adding the electrons from the S and the P together. How many electrons they would have, okay? Let's see. So this here basically just shows us that. So like sodium has 1 valence electron. So this is called the Lewis symbol. So to represent that valence electron, we use a single dot. That kind of makes it easier for us to do it rather than having to write out that long electron configuration. All we have to do is write sodium with a dot. And that lets us know that we have 1 electron that we can actually use for a reaction. Here we have magnesium. Magnesium has 2 dots. It has 2 valence electrons. And so this would be the highest energy configuration for sodium, which is NS1, because it only has 1 electron. It's going to be on that S. This guy has 2 electrons. It's going to be 2 on the S. Right? Aluminum has 3. So it has 2 in the S, 1 in the P. Silicone has 4. 2 in the S, 2 in the P. Phosphorus has 5. 2 in the S, 3 in the P. 5 dots around it. Sulfur has 6, 2s, 4p, 6 dots around it. Chlorine has 7, 2 in the S, 5 in the P, 7 dots around it. And then argon, which is a noble gas, has 8. So noble gases are going to have 8 around them. Halogens, which are group 17, are always going to have 7 around it. Okay. Okay, so we'll write the electron configuration for the highest occupied energy level for group 16. Group 6A is the same thing as group 16. Group 6A just stands for that main group. So if we go back to that last slide, what group was it? Group 16. So group 16, the highest energy electron configuration. That's your answer. Okay, so it's going to have 2 in the s orbital. So regardless of what period it's in, you're always going to have 2 in the s orbital, and you're going to have 4 in the p, right? So group 16, let's look at the periodic table. Come on now. Okay, so these are group 16s right here, all of these guys. So if we look at the S, that's 1, 2 in the S, and then 1, 1, 2, 3, 4 in the P, right? And that's always going to be the case if we go down that group. Okay, questions? Concerns? Okay. Identify the group whose electron configuration for the highest occupied energy level is NS2, NP2. Group 14, that's correct. Okay, so we talked about the Lewis symbol. Okay, so again, it just represents those valence electrons that we're able to use for the reactions. So for example, tellurium. How many valence electrons does tellurium have? It has 6. So then we'd have 6 dots around it. Now, when you put your dots, you don't want to put all your dots on one side. So you don't want to do it like this. Okay, you don't want to do it like that. So you can distribute them to here, because remember, each orbital holds how many electrons? 2. So in the case, you have 4 orbitals that are existing that are going to be used, right? 2 of them are going to have 2 electrons already occupied in them. In this case, you're going to have one that's going to be here and one that's going to be there. Okay, so let's talk about some trends. Okay, so if we look at the periodic table and the elements on the periodic table, as we move from left to right, the atomic size decreases. As we move from top to bottom, the atomic size increase. Now, the reason that this is the case is because of the nuclear charge. The more protons you have in the nucleus, the tighter it's going to be pulling those electrons. Okay, so if we take a look, my periodic table. So if we take a look, as we go from left to right, it's going to get smaller, right? Because it has more protons. So hydrogen is going to be bigger than helium, okay? As we go from top to bottom, it's going to get bigger because you're adding layers to it. So who's going to be my biggest atom and who's going to be my smallest atom? Sure. Nope, it's not going to be my biggest. Nope. Because remember, it increases in size. I mean, it decreases in size as we go from left to right. So it gets smaller as we go from left to right. So then who's going to be my biggest? My biggest. No, as we go down the periodic table, it's going to increase. So it gets smaller this way, smaller, going this way. So who's going to be my smallest atom? Helium, okay? Helium is going to be my smallest. And who's going to be my biggest? Now remember, it increases. As we go down, it increases. That's right. So francium is going to be bigger than OG, right? Okay. That's right. That's right. So francium is going to be our biggest and helium is going to be our smallest. Okay. So, and this is just kind of showing you that. Now, of course, there's going to be exceptions, right? But for the general trend, this is the general trend, okay? So we increase from this direction to this direction. So as we go from our noble gases to our metals, it's going to increase. And then as we go from top to bottom, it's going to increase, okay? So now knowing that, refer to the atomic table and list the atomic numbers 15, 16, and 33 in order of increasing atomic size. First off, what atomic numbers, what elements are atomic numbers 15, 16, and 33? Okay, so we know that this guy is phosphorus, this guy is sulfur, and this guy is arsenic. Okay, so then who's going to be the smallest? Sulfur. Okay, so sulfur is going to be the smallest. And then phosphorus, and then arsenic. Okay, Pac-Man eats the bigger one. So if we did this in terms of atomic number, okay. Okay, first ionization energy. Ionization energy is the energy to remove a single electron from a neutral gaseous atom of an element. Okay, so what does that mean? Okay, so if you kind of think about it, who are the electrons that want to lose electrons? I mean, who are the atoms that want to lose electrons? What was that? The big ones, okay, so big ones are going to be more apt to lose, okay, and you don't remember who wants to get rid of an electron? What was that? I said who wants to lose electrons? Which group wants to lose electrons? Group 1 and 2, right? How many electrons does group 1 want to lose? 1. Okay, so it's going to be really anxious to lose it. So it's not going to have a high ionization energy, right? Where fluorine on the other side, let me pull up my periodic table again. Fluorine on the other side wants to gain an electron. So is it going to want to lose an electron? No, because it needs 1 electron to be like a noble gas. It wants to gain 1 electron. So it's not going to be apt to lose anything. And then you have something like helium, who's like, I'm perfect the way I am. I'm just perfect. So is it going to want to lose an electron? No. Okay, so those are going to have high ionization energy, right? So the higher the energy it is, the harder it is to pull that electron away. Okay, the lower the ionization energy, the easier it is to pull that electron away. Okay, so these guys are going to have low ionization energy. These guys are going to have high ionization energy. So it's going to increase from left to right. And then it's also going to increase, it's going to decrease from top to bottom. So we'll say increase from bottom to top. So francium is going to have the lowest ionization energy, right? It's going to be like, just dropping electrons left and right. So are you guys with me? Dropping a electron. Okay. Okay, so let's test your guys' skill on this then. Okay, so this here is just the general trend. So you guys can see helium has the highest ionization energy. Then we have neon down here. But if we follow it going from left to right, hydrogen, then helium. And then we have lithium, beryllium. Here's an exception, right? Then we have carbon, nitrogen. Here's another exception. Then we have fluorine, and then neon. Neon has a higher one than fluorine. So, okay. For second ionization energy is the energy required to remove an electron from an ion with a +1 charge. So it's already lost 1 electron, right? And so the ionization energy to remove another electron from it. So that would be the second ionization energy. Third ionization energy would be where you have an ion that has a +2 charge. So this is the general trend for first ionization energy. Here's your question. List each of the following groups of elements in the order of increasing first ionization energy, B, E, N, and F. So who's going to have the lowest ionization energy and who's going to have the highest ionization energy? Put your mask on. Okay, so what's going to be the order? So BE, then F. Okay. Piece of cake. Good. Okay. So we've already talked about chemical families. We know that groups are going to behave the same way. They're chemical families. So alkali metals, group 1 metals, those guys are going to behave the same way. They have the same number of valence electrons. They have 1 valence electron. So they're going to form a +1 ion when they form ions, form a cation. So when I say they behave similarly, they behave similarly. So here we have lithium reacting with water. It gets all hot and smoky, hot and bothered. Then we have sodium. Sodium is right underneath, right? With water. It's nice, a nice little explosion going on, right? Potassium, which is underneath that, reacting with water. It's even more reactive, right? These are the halogens. So this is chlorine reacting with phosphorus, nice explosion. This is bromine reacting with phosphorus. Again, a nice explosion. Here we actually use zinc because iodine with phosphorus is very, very explosive. So they didn't show that. No, not yet. Okay, so you guys are already familiar with this because you guys have a beautiful periodic table that actually tells you the alkaline metals, the transitional metals, the lanthanoids, the actinoids, the halogens, the pictogens. So you have all of that on your periodic table. So alkaline metals or earth metals, they're going to have 2 valence electrons. They're going to form a cation that has a +2 charge when they form ions. Halogens have 7 valence electrons. They are going to form a -1 charge when they form an ion. They're going to be an anion. This here is just showing you the different metals, the alkali metals and alkaline metals. These guys are more reactive than these guys. These guys are also, your group 1 metals are more malleable, more ductile. So they're going to have more metallic characteristics. So as we go from right to left, we're going to become more metallic, which makes sense because on the right-hand side, we have the non-metals. On the left-hand side, we have the metals. So we have noble gases, which are going to be non-reactive. So they're going to have 8 valence electrons, or they're going to be full. So these are the halogens. So that's a group there, group 17. So we know what metals are. We've talked about non-metals and we've talked about metalloids. Metalloids have characteristics of both metals and non-metals. Non-metals are dull, they're brittle, they are poor at conducting heat and electricity, where metals conduct electricity great. They're malleable, they're ductile, they're lusty, you know. So these are your characteristics and chemical and some physical characteristics of metals and non-metals. So metals, they tend to lose electrons, so they form cations. Non-metals tend to gain electrons, so they form anions. So you'll have 1, 2, or 3 valence electrons. They're low ionization energy. They form compounds with non-metals, but they don't form with other metals. They form alloys. We'll get to that later. They have high electric conductivity. They have high thermal conductivity. They're malleable. Basically means that you can pound them out into a nice little sheet, right? And they're ductile. That means that they can be drawn out into like wires. So you can stretch them out so they form like wires. Non-metals, As I said, they tend to gain electrons. And for anions, they have 4 or more valence electrons. They are high ionization energy. They form compounds with metals and with other nonmetals. They're poor. They have poor electric conductivity, except for carbon when it's in a graphite form. We'll touch on that later on. They're poor thermal conductivity, but they're great insulators, like styrofoam cups. They're brittle and they're non-ductile. Okay, questions, concerns? You should know them. There'll definitely be test questions that deal with, but a lot of it is kind of makes sense. You look at a periodic table, oh yeah, this is going to have a plus charge, and this is going to have a minus charge though. Okay, these are your metals and non-metals, and your metalloids are right here. This here is looking at metallic characteristics. So metallic characteristics increases as we go from right to left. And then also it increases as we go from top to bottom. Questions? Concerns? Kool-Aid? Okay, well, that's all I got for you for today, because I know that you guys all need to do your practice exam and start working on that exam, right?